this is a really cool application of friction. I'm going to put masses on opposite sides of this string that's around this gold-plated cylinder here. And just to show you that it's not glued on, okay, if I don't put a mass on one side, it does that. So this mass is worth how much? Can you read it? Is that 20?
Yeah, 20 grams.
20 grams. Sue him if that's right. Okay, and this one is bigger, so it must be worth like 50 or something, right?
Yeah, it looks like 50.
50. Okay, so stop that. Okay, so why isn't the acceleration pulling the heavier mass down? Yeah, there's some friction up here which must be opposing that motion. So we have our ways. Now we add more mass. Okay, that didn't work. So let me give friction more of a chance. So I'm going to increase the path length for the friction to operate. Oh, that's nice. Yeah, nice, but not good enough. Okay. But
I believe in you, friction.
I don't.
oh, she of little faith. Okay. So, yeah, it's no fair tying a knot. That's really cheating. We shouldn't need to cheat. So let me wrap one more time. Okay? So by increasing the length, we can build up a really big friction force from not much, right? That's pretty handy. So let's see if we can understand how that works. So I'm not going to give you this question. You can relax. Okay, and now we're going to derive. Sorry, but this is too cool. Okay, so I want to blow up a portion of the string. So I'm going to have a large drawing that shows a little bit of curvature. So I want to consider this part of the string. And I'm going to use our usual 5-step program of drawing the picture and then isolating and working out the equation of motion. So I'm going to call this little bit of angle d theta, just like that little bit of angle. And there's going to be some tension down here in the string, and that's the tension at theta minus d theta, because I'm going to take theta as positive in the conventional direction. And up here, the tension is going to be, well, I already have it, t at theta plus d theta. And what other forces? Which way is friction going? I'm assuming that this one it's trying to yank it this way, so the frictional force is going to oppose that motion, and so friction here will be a little bit dF. And because these are inclined a bit with respect to the vertical, there will need to be a normal force so that this little segment of mass doesn't accelerate to the left. So I'll have a little bit of a normal force. So I want to check. Are we good with the setup so far? Because you're going to get uncomfortable in a moment. Why is it dn and df instead of just n and f? Can I defer that one for just a little bit? We will answer it. Yeah?
So why is, remind me why the force is going down.
So it depends on which way I'm yanking. So I'm assuming that I'm yanking, I'm trying to get it to go that way.
Okay, so
And so the frictional force is going to oppose that.
okay, so we're assuming that.
Tension's going to be increasing going around to positive theta.
Okay.
Okay? It will work either way, of course. Okay, so that's actually an excellent question. Why am I using differentials? Because I'm going to be taking a limit where this angle is really small. So the amount of the little rope is going to be going to 0, and so the frictional force that it can supply is not going to be a finite quantity. It's going to be going to 0 too. Okay, so if you're happy with a yes, sir, Christian. Yeah, so theta would be going around like that. Okay? Good question. Other questions? Okay, now I have to rely on Taylor. So T, wait. Do we have a Taylor in this class? Damn. Okay. So the derivative means the rate of change of the quantity, in this case the tension, with respect to the angle. That's saying that the tension a little bit away from the angle theta will be the value at theta plus the little change given by the rate of change, d theta times the little bit of angle. Okay? If the little bit of angle isn't a little bit, it's actually big, then do I have more terms that I have to include in a Taylor series expansion? Yeah. This is the first two terms in a Taylor series expansion. Just to humor you, don't freak out, Jessica. 1 over 2 factorial. Yeah, she's shaking her head violently from side to side. But you don't have to, we won't need that. But you could in order to get a finite. But it's the first, we really only need the first two terms of a Taylor series expansion because in the limit as d theta goes to 0, this term will disappear more rapidly than that and we won't require it. Okay, so I want a coordinate system that agrees with my drawing. It's probably x to the right and y up. And I'm going to have to sum the forces in both. So the sum of the forces in the x direction, and it's not supposed to move, I hope it's 0. Sum of the forces in the x, what is that? So dn is the easy one. That's definitely aligned with the x direction. What about the tension forces? Do they have any x component? Yeah, they have a little one, right? Not very big. So little one, Ian, try again. So t at theta plus d theta, that's this one up here, and the angle up here would be how much? How much is this angle there? Okay, here it's straight up and down. There it's d theta. So I would need which? Sine or cosine of d theta? Sine, right. Okay, so I have this sine of d theta. I hear some, is there a question? Oh, okay. So this force, this tension force is tipped back to the left through an angle d theta. That one right there is d theta. So it has a little bit of an x component in the negative direction, hence the negative. I got another one that's going to be t at theta minus d theta times the sine of d theta. Anything else in the x direction before I run out of room? Anissa, are you good? Anything else? No? Okay, that's a 0. But I can now use my expression here from the first two terms of the Taylor series expansion, dn minus, this is going to be t at theta plus t prime at theta d theta. If the angle is small, what does sine of the angle collapse to?
The angle itself.
Just the angle, as long as what?
Oh, the angle is small.
We're measuring in radians, that's right. So this is going to be like d theta minus, so I could say it's going to be approximately, we'll get to an approximate equals in a second, t at theta minus t prime at theta d theta. And again, sine of d theta is about d theta. Okay. Oh, that's cool. Look what happens to the derivative term.
Goes away.
Yeah, it wipes out because we have one that comes in with a negative sign and the other that comes in with a positive sign. So those are gone, and I just get 2 t of theta times d theta. So dn minus 2t at theta d theta is about 0. And in the limit that d theta goes to 0, it's exact. So I can use the dn in order to get the static friction force at maximum. So now I need to worry about the y direction. Some of the forces in the y direction also better be 0 if it doesn't slip. What are the forces in the y? Okay, so that's not so bad. T of theta plus d theta times what? Cosine? Cosine of d theta minus t at theta minus d theta cosine minus df. Yeah.
What exactly are we looking
Sorry?
for? What exactly are we looking for?
Ian wants to know, what are we looking for? I think spiritual satisfaction,
Sounds good. Sounds amazing.
growth, a good meal, a fine wine. No, not for you guys. We're looking for the equation that is satisfied by the tension so we can understand how wrapping a few more times around allows it to hold so well. Good question. Okay, now, what are you going to, I need help simplifying the cosine of d theta. Yeah.
Would you want to move like harder out of the way?
Well, I hope I'm strong enough. So cosine as the angle goes to 0 is like basically 1. The first correction would come in as d theta squared. Stop me if you've heard this one before. Cosine of theta, 1 minus theta squared over 2 factorial plus, and so on. Have you seen the Taylor series expansion for cosine? Yes, okay. So I can ignore this because it's going to involve d thetas squared compared to the ones that only involve d theta. So I'm going to write out t at theta plus t prime at theta d theta times 1 minus t at theta minus t prime at theta d theta times 1, oh, what the heck, equals df. Now the other terms wipe out. This goes away, and we get twice t prime theta d theta is equal to df. Almost done. If it just is on the verge of slipping, so the maximum static friction force will satisfy df is equal to mu sub s dn. Agreed? That's the limit. A little bit more and it's going to slip. So I have 2 t prime of theta d theta is equal to mu sub s. What was dn again? dn was 2t of theta d theta. Cool. The 2's go out. And I have d tension d theta is equal to mu sub s t of theta. So I can separate variables again and integrate dt over t is equal to the integral of mu sub s d theta. So the limits would be, for instance, from an angle that I'd start at contact, so that might be like 0, up to some final angle. And the tension would start at whatever is the minimum value that is established by this little weight. So I'll call it a t naught, up to some final t. And I get the logarithm of t minus the logarithm of t naught is equal to mu naught s times theta. Okay, and while I'm horsing around here, I'm going to cue up the main projector. Hello. So I simplify the logarithm. Log of t over t naught is equal to mu sub s theta, and I exponentiate. T over t naught equals e to the mu sub s theta, or the tension in the string as it wraps around grows exponentially with the angle. That's pretty cool. And that's how the tension force can get so large. saved by... Well, yeah, it's beginning. Okay, so now I want to tell you about... Yes, Claire? T naught would be... So you see I have a little mass... I mean, maybe it's hard to see. I have a little mass there to try to establish a little tension on one side. And then as it wraps around, the tension is growing like that, exponentially. So what was this one? 20, right? I think, so T naught would be like 20 grams times G, if I can ignore the mass of the string. All right.